In January of 2010, a physicist named Radu Coldea walked into a lab at the Helmholtz Zentrum Berlin and found something that should not exist. He had spent nearly a decade preparing for this moment. The crystal was cobalt niobate, a compound of cobalt and niobium arranged in long one-dimensional chains, each cobalt atom acting like a tiny bar magnet that could point up or down. His team had cooled it to 40 millikelvin, that is 40 thousandths of a degree above absolute zero, colder than deep space, colder than anything in the natural universe. They aimed a beam of neutrons at the crystal and slowly increased the strength of a magnetic field perpendicular to the chains, pushing the system toward a threshold called the quantum critical point, the exact boundary between magnetic order and quantum chaos, where the atoms stop behaving like individual magnets and begin vibrating together in collective quantum excitations that have no classical analog. At 5.5 Tesla, the system crossed that threshold, and in the scattering pattern of those neutrons, in the energy spectrum of the vibrations that emerged, two sharp resonance peaks appeared, two frequencies, two notes. Coldea measured the ratio of their energies. It was 1.618. The golden ratio. You know this number, or you think you do. You have seen it in documentaries about the Parthenon. You have seen it overlaid on the Mona Lisa, on Nautilus shells, on spiral galaxies, on the human face. You have been told it is the secret code of beauty, the hidden architecture of nature, the divine proportion that connects art and mathematics and biology in one elegant formula. You have absorbed this story so thoroughly that it feels like settled knowledge, like something science confirmed long ago and moved on from. Almost none of it is true. The golden ratio is not in the Parthenon. It is not in the Mona Lisa. It is not in the human body in any meaningful way. Those claims were fabricated, traceable to a single German psychologist in 1854 who measured over 100 cadavers and declared he had found a universal law of beauty. His name was Adolf Zeissing, and the mythology he created has been debunked repeatedly and thoroughly by mathematicians for over 30 years. And yet, it persists. It is still taught. It is still repeated in videos with millions of views. The golden ratio mythology is one of the most successful scientific frauds of the modern era, not because anyone is deliberately lying, but because the story is so satisfying that nobody bothers to check. But here is the part that should disturb you. The golden ratio is real. It does appear in the physical world, not where you were told to look, but in places far stranger and far more unsettling, in the quantum vibrations of matter cooled to the edge of absolute zero, in the atomic structure of crystals that were supposed to be mathematically impossible, in the mass spectrum of something called E8, a mathematical object so complex that merely mapping its structure required a matrix larger than Manhattan. And in every one of these places, the golden ratio does not appear approximately, or with some hand-waving about measurement tolerances. It appears exactly, because the mathematics demands it. You were told a fairy tale about a beautiful number that shows up everywhere. The truth is a different story entirely. The golden ratio shows up almost nowhere you were told it does, and everywhere you were never told to look. And the places where it actually appears suggest something about the structure of reality that is far more uncomfortable than any myth about Greek temples. Coldea himself seemed to sense the weight of what he had found. He is a quiet man, Romanian-born, a professor of physics at Oxford and a fellow of Lincoln College. He earned his doctorate at Oxford, did postdoctoral work at Oak Ridge National Laboratory and the Rutherford Appleton Laboratory, and won the BTM Willis Prize for neutron scattering in 2008. He is not someone who reaches for grand pronouncements, but describing the experiment, he said something that reveals how deeply the result unsettled him. It reflects a beautiful property of the quantum system, a hidden symmetry, actually quite a special one called E8 by mathematicians, and this is its first observation in a material, a hidden symmetry. Those two words carry an enormous implication. The symmetry was not imposed, it was not expected. It was there, in the material, waiting to be found, and it had been predicted by a Russian theoretical physicist 21 years earlier in a paper that almost nobody had read. This is the story of the most misunderstood number in mathematics, and what happened when it was finally found in the one place nobody expected. For 170 years, the golden ratio has been dressed in a costume it never asked to wear. The costume was sewn by one man, and the fact that you have probably never heard his name tells you something about how deeply his fabrication has embedded itself in the culture. His name was Adolf Zeising, born September 24th, 1810, in Ballenstedt, Germany. He was not a mathematician. He was not a physicist. He was a psychologist and philosopher who worked as a schoolteacher until gaining financial independence in 1853. 1 year later, he published a book with a title that tells you everything you need to know about his ambition. Translated from German, it reads, "A new theory of the proportions of the human body developed from a basic morphological law which stayed hitherto unknown, and which permeates the whole nature and art." Zeising had measured cadavers, over 100 of them, male and female. He claimed to have found that the navel divides the human body in the golden ratio, that the ratio of total height to navel height is approximately 1.618. From this single observation, he built a cathedral of speculation. He extended the golden ratio to animal skeletons, plant stems, crystal structures, chemical compounds, musical intervals, and planetary orbits. He declared it, in his own words, the universal law in which is contained the ground principle of all formative striving for beauty and completeness in the realms of both nature and art, and which permeates, as a paramount spiritual ideal, all structures, forms, and proportions, whether cosmic or individual, organic or inorganic, acoustic or optical. That is a school teacher who measured corpses, declaring he had found the secret of the universe. And the academic world ate it up. Before Zeising, nobody had claimed to find the golden ratio in Greek architecture or Renaissance painting. This is documented. German scholars have traced the historiography, and the conclusion is clear. The association between the golden ratio and ancient art did not exist before 1854. Zeising invented it. His posthumous book, Der Goldene Schnitt, published in 1884, continued the campaign after his death. Then the chain of transmission took over. Gustav Theodor Fechner, the experimental psychologist, ran rectangle preference experiments in the 1860s and 70s, claiming people preferred golden rectangles. Attila Gica, a Romanian prince and diplomat, born September 13, 1881, in Iași, Romania, great-grandson of the last reigning prince of Moldavia, published Esthétique des proportions dans la nature et dans les arts in 1927. Geiger wrapped Zeissing's claims in aristocratic elegance, elaborate geometric diagrams, and the kind of vague mathematical sophistication that impresses people who are not mathematicians. His influence was enormous. Salvador Dali explicitly used the golden ratio in The Sacrament of the Last Supper in 1955, painting it on a canvas shaped as a golden rectangle with a dodecahedron hovering over the scene. After reading Geiger, J. Hambidge, a Canadian-American artist, developed his dynamic symmetry theory. Le Corbusier based his entire modular proportioning system on the golden ratio in 1948. And by the time Dan Brown put the golden ratio into the Da Vinci Code in 2003, the myth was so thoroughly embedded in popular culture that questioning it felt like questioning gravity. Stanford mathematician Keith Devlin has been fighting this mythology for decades. He is the executive director of H-Star at Stanford, NPR's math guy, and one of the most publicly visible mathematicians in the English-speaking world. In a 2015 interview with Fast Company, he summarized the entire situation in 2 sentences. The link between the golden ratio and aesthetics comes primarily from 2 people, one of whom was misquoted, and the other of whom was just making shit up. The misquoted person was Luca Pacioli, the 15th century Franciscan friar who wrote De Divina Proportione. Pacioli called the ratio divine for theological reasons. He did not prescribe it as an aesthetic rule. The misattribution of a phi-based aesthetic theory to Pacioli was traced by Mario Livio to an error made in 1799. For over 200 years, people have been citing Pacioli as evidence that the Renaissance masters knew the golden ratio was beautiful. He never said that. The person who was just making shit up was Zeissing. Devlin compared golden ratio beliefs to UFOs, flat Earth, moon landing hoax, climate change denial. Harsh, but the data supports him. So let us go through the claims, one by one. The Parthenon. George Markowski, a computer scientist at the University of Maine with a BA from Columbia and a PhD from Harvard who worked at IBM's Thomas J. Watson Research Center from 1974 to 1984, addressed this directly in his 1992 paper, Misconceptions About the Golden Ratio, in the College Mathematics Journal. He opened the paper with a statement that should be printed on every pop science article about phi. Generally, its mathematical properties are correctly stated, but much of what is presented about it in art, architecture, literature, and aesthetics is false or seriously misleading. The actual dimensions of the Parthenon are 228 feet and 1/8 of an inch long by 101 feet and 3 3/4 inches wide. That is a ratio of 2.25, which is exactly 9 divided by 4. Not phi, not close to phi. The height of the facade, including the now destroyed triangular pediment, is approximately 45 feet and 1 inch. Markowski noted that drawings showing the Parthenon fitting in a golden rectangle invariably have parts of the building falling outside the rectangle, or include the steps below but not the platform, or exclude the pediment, or are simply drawn inaccurately. And reconstruction work from the 1980s revealed that the Parthenon has virtually no straight lines. Every column, every step, every surface is subtly curved for optical correction. The building is a masterwork of visual trickery, not mathematical mysticism. A comprehensive archaeological survey of 15 temples, 18 monumental tombs, 8 sarcophagi, and 58 grave stelae from the 5th century BC to the 2nd century AD concluded that the golden ratio was totally absent from Greek architecture of the classical 5th century BC, and almost absent during the following 6 centuries. The proportional system the Greeks actually used was based on simple integer ratios, particularly 4:9 and the 3-4-5 right triangle. No surviving Greek text mentions the golden ratio in an aesthetic context. The symbol phi itself was not adopted until around 1914, when American mathematician Mark Barr proposed it, supposedly in honor of the sculptor Phidias, 23 centuries after the Parthenon was built. The Great Pyramid of Giza, this one is more subtle because the numbers are tantalizingly close. The original base was approximately 230.4 meters. The original height, approximately 146.5 meters. Mario Livio computed the ratio of slant height to half base length as 612.01 divided by 377.90, which equals approximately 1.62. That is within 0.1% of phi. But the explanation has nothing to do with the golden ratio and everything to do with the Egyptian seist system. A secant is a measurement of gradient. For every 7 palms of vertical rise, the base extends a certain number of palms horizontally. The Great Pyramid was built with a secant of 5.5. That produces a height to half base ratio of 7 divided by 5.5, which equals 1.2727, and the square root of phi happens to be 1.2720. The corresponding slopes are 51.84 degrees versus 51.83 degrees. The match is coincidental. No Egyptian mathematical text, including the Rhind papyrus from around 1650 BC, mentions the golden ratio. The original limestone casing stones that would allow precise measurement of the slope are almost entirely gone, and there is no evidence that the Egyptians knew the Pythagorean theorem. The only right triangle documented in their surviving mathematical papyri is the 3-4-5 triangle, the Mona Lisa. There is no documentation whatsoever that Leonardo da Vinci used the golden ratio in any painting. His illustrations for Pacioli's De Divina Proportione, first printed in Venice on June 1st, 1509 by Paganino Paganini, were drawings of 3-dimensional geometric solids, 59 full-page woodcuts of dodecahedra, icosahedra, truncated polyhedra, and calligraphic letter templates. They were not demonstrations of phi in painting composition. Leonardo's Vitruvian Man, drawn around 1490, is based on the proportional system of Vitruvius, which uses whole number ratios. Where you draw a rectangle around the Mona Lisa's face to find the golden ratio is entirely subjective. Livio demonstrated this beautifully by presenting what he called the numerology of the TV in his kitchen, measuring the screen diagonal, the height, the depth, and various other dimensions, combining them in different ways until he produced phi. His point was devastating. If you are allowed to choose what to measure and how to combine the measurements, you can find the golden ratio in anything. The Nautilus shell. Keith Devlin admitted in his 2007 MAA column that he had inadvertently perpetuated this myth while debunking others, which tells you how persistent it is. Clement Falbo at Sonoma State University actually measured Nautilus shells at the California Academy of Sciences in 1999. The growth factor ratios ranged from 1.24 to 1.43, averaging about 1.33. That is close to 4/3. not 1.618. He concluded, "It seems highly unlikely that there exists any Nautilus shell that is within 2% of the golden ratio." John Sharp confirmed in the Nexus Network Journal in 2002 that the golden ratio, rectangular spiral, and the Nautilus spiral simply do not match. Christopher Bartlett at Towson University measured 80 Nautilus shells from the Smithsonian collection in 2019. The Nautilus genus averaged 1.310. The crusty Nautilus species averaged 1.356, with a range of 1.261 to 1.348. The Nautilus shell is a logarithmic spiral, yes, but its growth factor is not phi. A true golden spiral triples in radius approximately every quarter turn and grows by a factor of about 6.85 per full turn. The Nautilus approximately triples per full turn. They are different shapes with different growth constants. This is verifiable by anyone with a ruler and a shell. And the human body, Zeising's original claim, the one that started everything. Keith Devlin put it plainly. The popular idea that the navel divides the human body in accordance with the golden ratio is false. The figures are close, but there is considerable variation. People come in wildly different proportions. A 2008 study found that the Marquardt beauty mask, a facial template based on the golden ratio used in plastic surgery consultations, was ill-suited for non-European populations and did not even describe ideal face shape for white women. A 2024 peer-reviewed paper found there is no convincing evidence that the golden ratio is linked to idealized human proportions or facial beauty. Markowski himself ran what should have been the definitive experiment on golden rectangles. He presented 48 rectangles with aspect ratios ranging from 0.4 to 2.5 and asked subjects to select the most pleasing one. The most commonly chosen rectangle had a ratio of 1.83, not phi. And when he tested rectangles with ratios clustered between 1.6 and 1.7, subjects could not reliably distinguish between them at all. The supposed aesthetic superiority of the golden rectangle is not detectable by the people who are supposed to find it beautiful. Markowski proposed a generous tolerance of plus or minus 2%, which would mean any ratio between 1.586 and 1.650 could be called golden. Even with that generous range, most of the claimed appearances fail. There is one more historical thread worth pulling, because it reveals how thoroughly the golden ratio's real history has been distorted. The book that is most often cited as proof that Renaissance artists used the golden ratio is Luca Pacioli's De Divina Proportione. Pacioli was born around 1447 in San Sepolcro, a small town in Tuscany. He became a Franciscan friar and earned a reputation as the finest mathematics teacher in Italy. He is sometimes called the father of accounting for his earlier work, Summa di Arithmetica, which codified the double-entry bookkeeping system. In 1496, Ludovico Sforza, the Duke of Milan, invited both Pacioli and Leonardo da Vinci to his court. The two men became close friends. Pacioli tutored Leonardo in Euclidean geometry. Leonardo illustrated Pacioli's book. De Divina Proportione was composed in 1497 and first printed in Venice on June 1st, 1509. It contains 3 parts. The first discusses the mathematical properties of the golden ratio and its relationship to the regular polyhedra, drawing heavily on Euclid's elements. The second is a treatise on architecture and the proportions of the human body, based on the system of Vitruvius. The third is an Italian translation of Piero della Francesca's work on regular solids, which Pacioli included without attribution, leading the art historian Giorgio Vasari to accuse him of plagiarism. The 59 full-page illustrations of geometric solids, drawn by Leonardo, are spectacular. They show the 5 Platonic solids and various Archimedean solids in both solid and skeletal form, with masterful use of perspective and shading. They are the only book illustrations Leonardo ever produced, but they are drawings of polyhedra, not demonstrations of the golden ratio in painting. Pacioli called the ratio divine for 5 specific theological reasons, which he enumerated explicitly. Its uniqueness, like God, its trinity of terms, AB and A plus B, like the Holy Trinity, its irrationality, like God's incomprehensibility, its self-similarity, like God's omnipresence, and its connection to the dodecahedron, the 5th Platonic solid, which Plato associated with the cosmos. He did not claim it was the secret of beauty. He did not recommend it for artistic composition. The aesthetic theory was put into his mouth by later interpreters who confused the book's existence with a recommendation that does not appear in its pages. Even the name golden ratio is relatively modern. The Greeks called it extreme and mean ratio. Euclid defined it in Book 6 of the Elements, around 300 BC. Pacioli called it the divine proportion. The term goldener Schnitt, golden section, first appeared in print in 1835 in the second edition of the textbook Die rein Elementar Mathematik by Martin Ohm, a German mathematician and brother of the more famous physicist Georg Simonyi Ohm. The symbol phi was not standardized until around 1914, when it was proposed by American mathematician Mark Barr, reportedly in honor of the Greek sculptor Phidias, who supervised the construction of the Parthenon. The association between Phi and Phidias, and therefore between Phi and the Parthenon, is thus baked into the very symbol we use for the number. It is circular. We named the number after the man who built the building we falsely claim was built using the number. The mythology is encoded in the notation. This matters because it illustrates how deeply the false narrative has embedded itself. Every time you write the Greek letter phi, you are invoking a connection between the golden ratio and ancient Greek architecture that is entirely spurious. The symbol itself carries the myth. Markowski, Livio, and Devlin have spent decades documenting the fabrication, and they have barely made a dent. The myth persists because it flatters 2 deep human desires: the desire to believe that beauty has a mathematical formula, and the desire to believe that the ancients possessed secret knowledge that has been lost. Both desires are comforting. Both are wrong. And both are contradicted by the actual history of the number and the actual measurements of the buildings. The real story of the golden ratio requires no flattery and offers no comfort. It offers something better, the truth. And the truth is that this number, stripped of its mythological costume, is more remarkable than any myth could make it. It is the number that the universe uses to organize matter at the boundary of existence, not because it is beautiful, because it is necessary. So the story you were told is dead. The Parthenon does not encode the golden ratio. The Mona Lisa does not encode the golden ratio. The Great Pyramid does so only by a coincidence of the Sikid system. The Nautilus shell does not even come close. The human body does not conform to it in any consistent or meaningful way. The entire mythology traces to a schoolteacher in 1854 who measured corpses and decided he had found God's favorite number, amplified by a Romanian prince who made it sound elegant, an architect who built buildings with it, and a novelist who made it a plot device. But that demolition is not the end. It is the beginning. Because if the golden ratio is not in any of those places, then a harder question demands an answer. Why does it appear with mathematical precision in sunflower seed heads? Why do pine cones count their spirals in Fibonacci numbers? Why does the angle between successive leaves on a stem converge on 137.5 degrees, the golden angle, across hundreds of plant species? Why, when a materials scientist looked at an aluminum manganese alloy through an electron microscope in 1982, did he see a symmetry that the golden ratio saturates at every scale? The myths are dead, but the real mystery is just starting. The reason the golden ratio appears in plants has nothing to do with beauty. It has to do with a mathematical property so fundamental that it took until 1891 for a mathematician to prove it, and its implications are still making physicists uncomfortable today. Take a sunflower. The seeds in a sunflower head are arranged in two families of spirals, one winding clockwise and one winding counterclockwise. Count them. In a typical sunflower, you will find 34 spirals in one direction and 55 in the other. In a larger sunflower, 55 and 89. In a smaller one, 21 and 34. Those are consecutive Fibonacci numbers every time. Pine cones show 5 spirals one way and 8 the other, or 8 and 13. Pineapples have 3 families of spirals, 8 gently sloping, 13 steeper, 21 very steep field daisies typically have 13, 21, or 34 petals, and the divergence angle between successive leaves on a stem, the angle of rotation between one leaf and the next on the same branch, converges on 137.507, 764 degrees across hundreds of species. Elm and linden use a half turn between leaves. Beech and hazel use a third. Oak and apple use 2/5. Poplar and rose use 3/8. Willow and almond use 5/13. Every single one of those fractions is a ratio of consecutive Fibonacci numbers. That is 360 degrees divided by phi squared. It is called the golden angle. This is not numerology. This is botany confirmed by experiment. And the explanation is not mystical. It is mechanical. But the mechanism reveals something about phi that changes everything you think you know about why this number matters. The story starts in 1202, when Leonardo of Pisa, a man who would posthumously be called Fibonacci, meaning son of Bonaccio, published a book called Liber Abaci, the Book of Calculation. In chapter 12, he posed a problem about rabbits. Start with one pair. Assume each pair takes 1 month to mature and then produces one new pair every month after that. Assume no rabbits die. How many pairs do you have after 12 months? The answer is 144, generated by the sequence 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144. Each number is the sum of the two before it. The term Fibonacci sequence was coined by the French mathematician Édouard Lucas in the 19th century. The sequence itself was known to the Indian mathematician Pingala around 200 BC in connection with Sanskrit poetry meters. The connection to the golden ratio is exact. The ratio of consecutive Fibonacci numbers converges on phi. 5 divided by 3 is 1.667. 8 divided by 5 is 1.6. 13 divided by 8 is 1.625. 21 divided by 13 is 1.615. The oscillation dampens and approaches 1.61803 from alternating sides, and a formula proved by Jacques-Philippe Marie Binet in 1843, though known earlier to Euler and Daniel Bernoulli, gives the nth Fibonacci number exactly in terms of phi. F of n equals phi to the n minus ci to the n, all divided by the square root of 5, where psi is the conjugate of phi, 1 minus root 5 over 2, approximately negative 0.618. Since the absolute value of psi is less than 1, its powers shrink to nothing, and for large n, the Fibonacci numbers are simply phi to the n divided by root 5, rounded to the nearest integer. That is elegant, but that is just the arithmetic. The deeper question is, what makes phi special among all irrational numbers? Why this number and not pi, or the square root of 2, or e? Every irrational number can be expressed as an infinite continued fraction. Pi is 3 plus 1 over 7 plus 1 over 15 plus 1 over 1 plus 1 over 292, and so on. The partial quotients, those numbers in the denominators, determine how well the number can be approximated by fractions. Large quotients mean the continued fraction converges quickly, which means the number has unusually good rational approximations. Pi is well approximated by 22 over 7 because the quotient 7 is relatively large, and it is spectacularly well approximated by 355 over 113 because the quotient 292 is huge. The golden ratio has the continued fraction 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 forever. Every partial quotient is 1, the smallest possible value. This means phi's continued fraction converges more slowly than any other irrational number's continued fraction. Its rational approximations, which are the ratios of consecutive Fibonacci numbers, are the worst rational approximations you can get for any irrational number of the same denominator size. In 1891, the German mathematician Adolf Hurwitz proved the theorem that makes this precise. For any irrational number xi, there are infinitely many distinct fractions p over q, such that the absolute value of xi minus p over q is less than 1 divided by the square root of 5 times q squared. The constant root 5 is the best possible, and phi is the reason why. If you try to replace root 5 with any larger constant, phi becomes the first number to have only finitely many approximations satisfying the bound. It is the last irrational number standing. After removing phi and its equivalents from consideration, the bound improves to root 8, which characterizes root 2, then root 2210 over 5, and so on. This hierarchy is called the Lagrange spectrum, and phi sits at its extremal point. This is what it means to call phi the most irrational number. It is not a metaphor, it is not poetic. It is a theorem with a proof. Phi is the irrational number that is hardest to approximate by any fraction. Its convergence, the ratios of consecutive Fibonacci numbers, approach it, but they approach it more grudgingly, more stubbornly. more reluctantly than the convergence of any other irrational approach their target. And that stubbornness is why plants use it. If you arrange seeds at an angular offset that is a rational fraction of a full turn, like a third or 2/5, successive seeds eventually line up in radial spokes, and you get gaps between the spokes where space is wasted and sunlight is blocked. If you use an irrational fraction, the seeds never exactly repeat their angular positions, but some irrationals are close enough to simple fractions that you still get near alignments, ghost spokes that waste nearly as much space as real ones. Phi is the irrational number that is furthest from any simple fraction. The golden angle, 137.5 degrees, guarantees that no two successive seeds will ever even approximately line up. Every new seed falls in the largest available gap. The packing is as efficient as geometry allows. In 1868, the German botanist Wilhelm Hofmeister proposed that new growth elements, called primordia, always form in the least crowded spot on the growing tip of a plant. A simple rule: each new leaf or seed simply appears wherever there is the most room. In 1979, Helmut Vogel published a mathematical model in Mathematical Biosciences, Volume 44, pages 179 to 189, using polar coordinates and the golden angle to reproduce the exact spiral patterns seen in sunflower heads. And then, in 1992, two French physicists named Stéphane Douady and Yves Couder proved it with an experiment so elegant it belongs in a museum. They published in Physical Review Letters, Volume 68, Number 13, on March 30th, 1992. Their paper was titled Phyllotaxis as a Physical Self-Organized Growth Process. They let magnetized ferrofluid drops fall one at a time onto a magnetized dish filled with silicon oil. Each drop repelled the ones already there and drifted to the least crowded position, mimicking Hofmeister's rule for plant growth. As they varied the rate at which drops fell relative to how fast the dish expanded, the patterns that emerged spontaneously reproduced the Fibonacci phyllotaxis observed in sunflowers, pine cones, and pineapples. The golden angle was not programmed in. It emerged from the physics of mutual repulsion and sequential placement. They had built a mechanical sunflower, and it counted in Fibonacci numbers without being told to. Nature does not know about phi. Nature does not need to. Phi is simply what happens when a growth process seeks to avoid periodicity as thoroughly as possible. The golden angle is not chosen. It is the inevitable consequence of a system that places each new element in the emptiest available space. And there is something about that word, inevitable, that you should hold on to. Because that property, that stubbornness, that refusal to be pinned down by any fraction, is not just a botanical curiosity. It is the reason the golden ratio appears in the mass spectrum of the most exceptional symmetry in the classification of all possible symmetries. But that part of the story requires going somewhere even physicists would rather not go. First, though, you need to understand what happened on April 8th, 1982, in a laboratory at the National Bureau of Standards in Gaithersburg, Maryland. Because before the golden ratio appeared in quantum vibrations, it appeared in an impossible crystal, and the man who found it nearly lost his career for saying so. Dan Shechtman was born January 24th, 1941, in Tel Aviv, in what was then the British Mandate of Palestine. He earned his bachelor's degree in mechanical engineering from the Technion, Israel's Institute of Technology, in 1966, his master's in materials engineering in 1968, and his PhD in materials engineering in 1972. He did postdoctoral work at Wright-Patterson Air Force Base in Ohio from 1972 to 1975, where he studied the microstructure of titanium aluminide alloys. He joined the faculty at the Technion in 1975 and went on sabbatical to the NBS in 1981 to study rapidly cooled aluminum alloys. He was 41 years old, a mid-career materials scientist with a solid but not spectacular reputation. Nobody outside his immediate field knew his name. His colleague Frank Biancaniello had prepared the sample, 86% aluminum, 14% manganese, an alloy designated Al6Mn. The sample was produced by melt spinning, a technique that cools molten metal at about 1,000,000 degrees per second by ejecting it onto a rapidly rotating copper wheel. The resulting ribbon of metal freezes so quickly that its atoms do not have time to arrange themselves into the equilibrium crystal structure. Instead, they freeze in whatever configuration they happen to be in when the quench hits. This is how you catch unusual atomic arrangements, by freezing them before they can relax into normalcy. Shechtman placed sample number 1725 under a transmission electron microscope and looked at its diffraction pattern. Diffraction patterns reveal the atomic scale periodicity of a material, shine electrons through a crystal, and the regular spacing of atoms causes the electrons to scatter in specific directions, producing an array of bright dots whose symmetry reflects the symmetry of the atomic lattice. A cubic crystal produces a 4-fold pattern. A hexagonal crystal produces a 6-fold pattern. Those are the allowed symmetries. The crystallographic restriction theorem, proven rigorously in the 19th century, permits only 1-fold, 2-fold, 3-fold, 4-fold, and 6-fold rotational symmetry in a periodic crystal. 5-fold symmetry is specifically forbidden. The proof is simple. You cannot tile a plane with regular pentagons. There are always gaps, and a crystal is by definition a periodic tiling of 3-dimensional space. Therefore, no crystal can have 5-fold symmetry. This was textbook knowledge. It was considered as settled as the law of gravity. The diffraction pattern of sample 1725 showed 10-fold rotational symmetry, concentric rings of 10 bright dots at equal angular spacing. This is icosahedral symmetry, the symmetry of a regular icosahedron, a 20-faced solid with 12 vertices and 30 edges, the shape of a 20-sided die. Icosahedral symmetry contains 6 axes of 5-fold rotation. It was forbidden. What Shechtman was seeing could not exist. Next to the sample number in his lab notebook, he wrote 10-fold followed by 3 question marks. He muttered to himself in Hebrew, Ein chaya kazo, there is no such animal. He spent the rest of that afternoon trying to prove himself wrong. He rotated the sample to different orientations and found consistent icosahedral symmetry from every direction. He ran dark field imaging experiments to look for twinned crystals, a common artifact in which multiple ordinary crystals grow together at specific angles, mimicking higher symmetries. The dark field images were uniform, no twins. He ran convergent beam electron diffraction experiments, which probe the symmetry at a single point in the sample, rather than averaging over a large area. The local symmetry was icosahedral. Every test confirmed the same impossible result, and the golden ratio was everywhere in the diffraction pattern. In an icosahedral diffraction pattern, the ratio of distances between successive spots along any radial direction is phi. This is not an approximation. It is a geometric fact. The diagonal of a regular pentagon divided by its side equals exactly 1 plus root 5 over 2, which is phi. The icosahedron, the dodecahedron, and every structure with five-fold rotational symmetry encodes the golden ratio at every scale, in every proportion, in every distance ratio. Shechtman had not gone looking for phi. He had found a material that violated the most basic theorem of crystallography, and phi was woven into its atomic fabric, like a watermark you cannot remove without destroying the page. Nobody believed him. His research group leader at the MBS, a man whose name Shechtman has never publicly disclosed, told him to go back and read the textbook. Within days, the same man asked Shechtman to leave the group. The reason given was that Shechtman was bringing disgrace on the team. He was not fired from the NBS, but he was professionally exiled from his own research group for reporting what his instruments showed him. He returned to Israel and spent the next 2 years trying to get the result published. His initial manuscript was rejected. It was Ilan Blech, a colleague at the Technion, who became the first person in the world to believe the data and help develop a model for the icosahedral structure. Denis Gratius from the CNRS in France provided mathematical rigor, and John W. Kahn, a senior and highly respected material scientist at the NBS, agreed to put his name on the paper, lending it the credibility of his reputation. The paper appeared in November 1984 in Physical Review Letters, Volume 53, Number 20, pages 1951 through 1954. It was 2.5 years after the discovery, and the backlash was ferocious. Linus Pauling, the only person in history to win 2 unshared Nobel Prizes, attacked the result publicly and relentlessly. His exact words, delivered at conferences and in publications, were, "There is no such thing as quasicrystals, only quasi-scientists." This was not a private disagreement. Pauling was the most famous chemist alive, the president of the American Chemical Society, an idol to generations of scientists. He proposed that what Shechtman had seen was merely a crystal twin, multiple ordinary crystals intergrown at specific angles to mimic five-fold symmetry. Other crystallographers investigated this possibility and ruled it out. Pauling did not accept their conclusions. He published his own papers insisting on the twinning explanation. He maintained his opposition from 1984 until his death on August 19, 1994. He died still believing that quasicrystals did not exist. Shechtman later described the experience. "For a long time, it was me against the world. I was a subject of ridicule and lectures about the basics of crystallography. The leader of the opposition to my findings was the star of the chemistry community. He had won 2 unshared Nobel Prizes and believed strongly that what I claimed could not be." In his Nobel lecture in 2011, Shechtman showed a slide of a single cat walking with calm confidence past a line of 20 snarling German shepherds. The audience laughed, but the metaphor was precise. He had walked past the entire crystallographic establishment for nearly a decade, alone, with nothing but his data. He identified 5 factors that enabled the discovery: professionalism, tenacity, believing in yourself, and courage. Notice the order: the instrument first, then the training, then 3 qualities of character: The implication is clear. The microscope could show anyone the truth, but seeing the truth and reporting it when it contradicts the textbook are different acts entirely. The Nobel Prize came in 2011, 29 years after the discovery. Shechtman was the sole recipient. 10 million Swedish krona, approximately $1.5 million. The Nobel Committee citation stated, his discovery was extremely controversial. However, his battle eventually forced scientists to reconsider their conception of the very nature of matter. In 1992, the International Union of Crystallography had already changed its definition of crystal from a substance in which the constituent atoms, molecules, or ions are packed in a regularly ordered, repeating three-dimensional pattern, to one that could accommodate aperiodic order. The most fundamental definition in materials science had to be rewritten because of what one man saw through a microscope. There is a coda that is too perfect not to mention. In 2014, Dan Shechtman ran for president of Israel. He received exactly 1 vote. The Israeli press called him the quasi-president. At his Nobel banquet speech in Stockholm, he had declared, "Science is the ultimate tool to reveal the laws of nature, and the one word written on its banner is truth." The quasi-president remained committed to the banner. The theoretical framework connecting Shechtman's discovery to the golden ratio was built by Roger Penrose, who in 1973 and 74 developed his famous aperiodic tilings. Penrose was born August 8, 1931, in Colchester, Essex, the son of psychiatrist and geneticist Lionel Penrose, the brother of mathematician Oliver Penrose and 10-time British chess champion Jonathan Penrose. He earned a first-class degree in mathematics from University College London in 1952 and a PhD from Cambridge in 1957. The Penrose-Hawking singularity theorems proved that black holes form inevitably from gravitational collapse. His twistor theory remains one of the most ambitious attempts to unify general relativity with quantum mechanics. He created the impossible Penrose triangle with his father in the 1950s and exchanged ideas with M.C. Escher, influencing ascending and descending and waterfall. His tilings were a mathematical amusement that turned out to predict a new state of matter. Penrose showed that 2 simple tile shapes, a fat rhombus and a thin rhombus whose angles are multiples of 36 degrees, can tile an infinite plane without ever repeating. The pattern has no translational periodicity. It never recurs, but it is not random either. It has a precise, deterministic structure governed entirely by the golden ratio. The ratio of fat tiles to thin tiles as the tiling extends toward infinity approaches phi exactly. The spacing of hidden long-range order lines, called Amman bars, is in the golden ratio. The tile shapes themselves encode phi in their proportions. In 1982, crystallographer Alan Mackay took a Penrose tiling and computed its Fourier transform, the mathematical operation that converts a spatial pattern into its frequency components. The result showed sharp diffraction peaks with 5-fold symmetry. He had theoretically predicted, from pure mathematics, exactly the kind of diffraction pattern Shechtman observed from his aluminum-manganese alloy. And in December 1984, Dov Levine and Paul Steinhardt published the paper that coined the word quasicrystal, explicitly modeling the new materials as 3-dimensional analogues of Penrose tilings. Penrose's mathematical game had become a description of actual atomic structure. The first natural quasicrystal, was discovered in 2009 by Paul Steinhardt and Luca Bindi in a meteorite from the Katerka region of northeastern Russia. It was an aluminum copper-iron alloy called icosahedrite, and it was extraterrestrial in origin, approximately 4.5 billion years old. The golden ratio was encoded in the atomic structure of a crystal that formed before the Earth existed. In 1997, Penrose sued Kimberly-Clark Corporation over quilted toilet paper that resembled his tilings. The case was settled out of court. The most profound mathematical pattern connecting number theory, quantum physics, and the fundamental structure of matter was, briefly, also a bathroom product. Penrose won the Nobel Prize in Physics in 2020, not for his tilings, but for his work on black holes. He was 89 years old. The tilings that predicted quasicrystals, that encode the golden ratio, that bridge the gap between recreational mathematics and the structure of matter, were not mentioned in the citation. So by the end of the 20th century, the golden ratio had been found in 3 rigorously confirmed, experimentally verified, peer-reviewed domains: plant phyllotaxis, quasicrystalline atomic structure, and the mathematical framework of aperiodic tilings. In all 3 cases, it appeared not because someone went looking for it with a ruler and wishful thinking, but because the mathematics of the underlying system demanded it. Phi's extreme irrationality, its resistance to periodicity, its connection to fivefold symmetry through the geometry of the regular pentagon, forced it into these structures whether anyone wanted it there or not. But those were all, in a sense, geometrical appearances, spatial, about how things are arranged. What Radu Coldea found in 2010 was something categorically different. The golden ratio appeared not in the spatial arrangement of atoms, but in the energy spectrum of their collective quantum vibrations. Not in geometry, but in dynamics. Not in where matter sits, but in what it does when pushed to the boundary between order and chaos. And the symmetry that produced it was not fivefold or icosahedral. It was E8. And E8 is something that most physicists would rather not think about too carefully, because its existence raises questions about the deep structure of reality that do not have comfortable answers. To understand what Coldea found, you need to understand what E8 is. And to understand E8, you need to understand the question it answers. The question is, what are all the possible continuous symmetries that the universe could have? In the late 19th century, 2 mathematicians tackled this problem independently. Wilhelm Killing, working between 1887 and 1890, and Elie Cartan, in his 1894 doctoral thesis, classified all the simple compact Lie algebras. These are the mathematical structures describing continuous symmetries, the symmetries of smooth rotations and transformations that preserve some underlying geometric property. Their answer was remarkably clean. There are 4 infinite families labeled A, B, C, and D, each indexed by a positive integer. These correspond to familiar symmetries like rotations in n dimensions, symmetries of spheres, symplectic transformations. You can always make a bigger one by increasing n. They go on forever. But then there are 5 exceptions. 5 objects that do not fit into any infinite family. They are called G2, F4, E6, E7, and E8. They are the exceptional Lie groups. They exist because the classification, which is a rigid logical structure following necessarily from the axioms, requires them. They are not approximations or special cases of anything larger. They are standalone objects, irreducible, isolated, and necessary. Like prime numbers in the taxonomy of symmetry, E8 is the largest of the five. Its numbers stagger the imagination. It has dimension 248, not 3, not 4, not 10 or 11 like the extra dimensions of string theory. 248. Its root system consists of 240 vectors in 8-dimensional Euclidean space. These vectors come in two families, 112, from permutations of vectors with 2 entries of plus or minus 1 and 6 zeros, and 128 of the form plus or minus 1/2 in all 8 entries, with the constraint that the total number of minus signs is even. Total 240 roots. Its Weyl group, the discrete symmetry group of its root system, has order 696,729,600, nearly 700 million symmetry operations. Its Coxeter number is 30. Its exponents are 1, 7, 11, 13, 17, 19, 23, and 29. All the integers less than 30 that share no common factor with 30. Its smallest non-trivial representation is the 248-dimensional adjoint representation, meaning E8 acts on its own Lie algebra. This is unique among all simple compact Lie groups. E8 is, in some sense, its own explanation. It needs nothing outside itself to be described. In March of 2007, the Atlas of Lie Groups project announced that they had completed the first full computation of E8's character table. The computation finished at 9 in the morning on January 8, 2007, after running on a supercomputer at the University of Washington. The team of 18 researchers was led by Jeffrey Adams at the University of Maryland and included contributors from Cornell, MIT, Michigan, Utah, and Poitiers. One of the core members, Foucault Duclos, at the University of Lyon, had died in 2006 before the computation finished. He had written much of the software that made it possible and did not live to see the result. What they computed was the matrix of Kasdan-Lustig-Vogel polynomials for the split real form of E8. The matrix was 453,060 by 453,060, containing 60 gigabytes of data. If printed in 6-point type, it would cover an area larger than Manhattan. The largest polynomial coefficient was 11,808,808. E8 also appears in string theory, one of the two consistent 10-dimensional heterotic string theories discovered by Gross, Harvey, Martinek, and Rome in 1985, has the gauge group E8 times E8. This is not an arbitrary choice. It is forced by the requirement of anomaly cancellation. The mathematics of quantum consistency in 10 dimensions admits only a handful of possible gauge groups, and E8 times E8 is one of them. Take it away, and the theory becomes mathematically inconsistent. The equations collapse into contradiction, but the connection to the golden ratio does not come through string theory. It comes through a paper published in 1989 by a Russian theoretical physicist whose name you have almost certainly never heard, and whose prediction sat in the literature for 21 years before anyone confirmed it was true. Alexander Borisovich Zamolodchikov was born September 18, 1952, in Novo Ivankovo, a town now absorbed into the scientific city of Dubna in the Moscow region. He has an identical twin brother, Alexei Borisovich Zamolodchikov. The Zamolodchikov twins are one of the great partnerships in theoretical physics. Together and separately, They made foundational contributions to conformal field theory, statistical mechanics, and quantum field theory. Alexander co-authored the legendary BPZ paper in 1984 with Alexander Belevin and Alexander Polyakov, 3 Alexanders, which essentially created the mathematical framework of two-dimensional conformal field theory, one of the most influential papers in theoretical physics of the past half-century. He earned his PhD from the Institute for Theoretical and Experimental Physics in Moscow in 1978, supervised by Karen Ter-Martirosyan, and worked at the Landau Institute for Theoretical Physics, alongside Polyakov, one of the most fertile environments for theoretical physics in the late Soviet Union. He emigrated to the United States in 1990 and joined the faculty at Rutgers University, eventually holding the Board of Governors professorship. In 1989, Zamolodchikov published a paper in the International Journal of Modern Physics A, Volume 4, Number 16, pages 4235 through 4248. The title was Integrals of Motion and S-Matrix of the Scale T equals Tc, Ising Model with Magnetic Field. A companion paper appeared as Integrable Field Theory from Conformal Field Theory in Advanced Studies in Pure Mathematics, Volume 19. The paper considered the two-dimensional Ising model the simplest mathematical description of a magnet consisting of spins that can point up or down and interact with their neighbors at its critical temperature. At the critical temperature, the system is poised between ordered and disordered phases. Zamolodchikov asked what happens when you perturb this critical system with an external magnetic field. He showed that this perturbed field theory possesses non-trivial conserved quantities at specific spins: 1, 7, 11, 13, 17, 19, 23, and 29. If you recognize those numbers, you should. They are the exponents of E8. He then proved that the existence of these conserved quantities constrains the particle spectrum to exactly 8 massive particles, interacting through a bootstrap mechanism with mass ratios governed by the root structure of the E8 Lie algebra. The 8 predicted particles have specific mass ratios relative to the lightest. The first has mass 1, the second has mass 1.618, the golden ratio, the third approximately 1.989, the fourth approximately 2.405, the fifth approximately 2.956, the sixth approximately 3.891, the seventh approximately 4.783, the eighth approximately 5.205, and the golden ratio does not appear just once. It appears 4 times as a ratio between specific pairs: the second to the first, the sixth to the third, the seventh to the fourth, and the eighth to the fifth, all equal phi. The deep mathematical reason involves the relationship between E8 and icosahedral symmetry. The Coxeter group H4, the symmetry group of the 600 cell, the 4-dimensional analog of the icosahedron, is a maximal subgroup of the Weyl group of E8. The 600 cell is a 4-dimensional polytope with 120 vertices, and its rotational symmetry group has 7,200 elements. Its vertices, represented as unit quaternions, form the binary icosahedral group, and integer combinations of these quaternions map into 8-dimensional space as the E8 root lattice. The 4 lightest E8 particles correspond to the radii of 4 Gaussian circles formed by projecting E8 240 roots onto the Coxeter plane, and the 4 heavier particles are obtained by multiplying those radii by phi. The ratio of the 2 smallest Gaussian circle radii is phi. This was proven rigorously by MIT mathematician Bertram Constant in a 2010 paper in Selecta Mathematica. The golden ratio is in E8 because 5-fold symmetry is in E8, and 5-fold symmetry is there because H4 is a subgroup of E8's Weyl group, and the formula 2 times the cosine of pi over 5 equals phi connects pentagonal geometry to the Coxeter structure of the algebra. Every link in this chain is a mathematical necessity. Zamolodchikov published this in 1989, and then the predictions sat. For 21 years, his twin brother Alexei died on October 18, 2007, at the age of 55. Alexei had made his own landmark contributions to quantum gravity, Liouville field theory, and the C theorem. He did not live to see his brother's E8 prediction confirmed. Alexander won the 2024 Breakthrough Prize in Fundamental Physics, among many other honors, including the Danny Heinemann Prize for Mathematical Physics and the Lars Onsager Prize. He accumulated over 29,000 citations, but the E8 mass spectrum paper remained largely theoretical for 2 decades because no one had a material clean enough and a cryostat cold enough to test it. Radu Coldea had been thinking about this problem since roughly 2000. He knew that cobalt niobate, a material whose magnetic cobalt atoms form quasi-one-dimensional chains with ferromagnetic coupling along the chains and weak antiferromagnetic coupling between chains, was an excellent approximation to the one-dimensional quantum Ising model that Zamolodchikov's theory describes. The chains make the system effectively one-dimensional. The transverse magnetic field provides the perturbation, the quantum critical point, where the transverse field overcomes the exchange coupling and destroys the ferromagnetic order, provides the criticality. His team grew a single crystal of cobalt niobate. They cooled it to 40 millikelvin in a dilution refrigerator. They applied a transverse magnetic field perpendicular to the spin direction and slowly increased it toward the critical field at approximately 5.5 Tesla. As the field increased, the spin excitations changed character. In the ordered phase below the critical field, the excitations are pairs of domain wall kinks, boundaries between regions of upspins and downspins. As the field approaches the critical point, these kinks become lighter and begin to bind together into resonant states, quantum-bound states whose energies are determined by the confinement potential. At the critical field, the system enters the quantum critical regime, and the excitation spectrum is predicted to reorganize according to the E8 mass spectrum. They measured the spin dynamics using inelastic neutron scattering at 2 facilities: the BER-2 research reactor at the Helmholtz-Zentrum Berlin, which provided steady-state neutrons, and the ICIS pulsed neutron source at the Rutherford Appleton Laboratory near Oxford. As their press release noted, by combining the special expertise in Berlin whilst taking advantage of the pulsed neutrons at ICIS near Oxford, permitted a perfect combination of measurements. Alan Tennant at Berlin led the experimental group there. The combination of 2 complementary neutron sources was essential for resolving the fine structure of the excitation spectrum at the critical point. 2 sharp resonance peaks appeared in the low energy spectrum, just below the multi-particle continuum, where individual excitations blur into a soup of overlapping states. 2 distinct quasi-particles, two frequencies. Coldea measured the ratio of their energies, 1.618, the golden ratio, exactly as Zamolodchikov had predicted 21 years earlier. Not approximately, not within some generous tolerance, to the precision of the measurement. The first two E8 particles had masses in the golden ratio. Coldea described it carefully. Here, the tension comes from the interaction between spins, causing them to magnetically resonate. For these interactions, we found a series of resonant notes. The first two notes show a perfect relationship with each other. Their frequencies are in the ratio of 1.618, which is the golden ratio famous from art and architecture. And then, it reflects a beautiful property of the quantum system, a hidden symmetry. Actually, quite a special one called E8 by mathematicians, and this is its first observation in a material. Alan Tennant said, "Such discoveries are leading physicists to speculate that the quantum atomic scale world may have its own underlying order. Similar surprises may await researchers in other materials in the quantum critical state." The paper was published in Science, volume 327, issue 5962. Pages 177 through 180. On January 8, 2010, 9 authors, 3 years to the day after the Atlas of Lie groups completed its computation of E8. The prediction had waited 21 years. The mathematics was exact, and the universe obeyed. Think about the chain of events that had to occur for that measurement to happen. In 1202, Fibonacci published a puzzle about rabbits that produced the sequence 1, 1, 2, 3, 5, 8, 13. In 1854, Zeising measured cadavers and fabricated a universal law. In 1891, Hurwitz proved that phi is the most poorly approximated irrational number. In 1974, Penrose created tiles whose proportions are governed by phi. In 1982, Shechtman saw tenfold symmetry in an alloy and was thrown out of his research group. In 1989, Zamolodchikov predicted that the simplest magnet at criticality would produce 8 particles with E8 symmetry and a golden ratio, mass ratio. In 2007, Zamolodchikov's twin brother, Alexei, died. In 2010, Coldea measured the ratio at 1.618. Each of these people worked independently. None of them were trying to find the golden ratio. Fibonacci was teaching Hindu-Arabic numerals to European merchants. Hurwitz was proving a theorem about Diophantine approximation. Penrose was playing with recreational mathematics. Shechtman was characterizing aluminum alloys. Zamolodchikov was exploring integrable field theories. Coldea was studying magnetic phase transitions. The golden ratio was not their goal. It was their result. It emerged from the mathematics of each problem as an unavoidable structural constant, and only in retrospect does it become clear that all of these results are connected by a single mathematical fact. Phi is the number that most completely resists rational periodicity, and wherever nature demands aperiodic structure, phi is forced into the physics. There is something vertiginous about that convergence. A number that resists capture keeps appearing, unbidden, in the most unexpected places. A number defined by its refusal to be a ratio shows up as the ratio between quantum particle masses. A number defined by its distance from all rational numbers appears in the most rational enterprise humans have ever undertaken. which is experimental physics. The irony is precise. The most irrational number is the one that the universe most insistently tells us is real. And the history of its reception mirrors its mathematics. The genuine appearances of phi were ignored, ridiculed, or dismissed for decades. Shechtman was kicked out of his lab group. Zamolodchikov's prediction was not tested for 21 years. The fabricated appearances, the Parthenon, the Mona Lisa, the Nautilus shell, were embraced immediately and propagated without resistance. The false version of the golden ratio was easy to accept. The true version was hard. Just like the number itself, the truth about phi resists easy capture. You have to earn it the hard way, one painful approximation at a time. Now carry this forward to something that puzzled crystallographers for over a century. A crystal, by the classical definition that held from the 1830s to 1992, is a solid in which atoms are arranged in a pattern that repeats periodically in 3 dimensions. The crystallographic restriction theorem proves that such periodic arrangements can only have rotational symmetries of order 1, 2, 3, 4, or 6. The proof is elegant. If you have a lattice point and rotate it by some angle, the rotated point must also be a lattice point. The only angles that produce new lattice points at distances compatible with the original lattice spacing are multiples of 60 and 90 degrees, which correspond to 2-fold, 3-fold, 4-fold, and 6-fold symmetry. 5-fold rotation does not work because the distance between the original point and its image after a 72-degree rotation is incommensurate with the lattice spacing. The word incommensurate means precisely that the ratio of distances involves an irrational number, and that irrational number is phi. So the reason 5-fold symmetry is forbidden in periodic crystals is that it would require the golden ratio as a structural ratio, and the golden ratio, being irrational, is incompatible with periodicity. The golden ratio does not just happen to show up in 5-fold symmetry. It is the reason 5-fold symmetry is forbidden in periodic structures. And when Shechtman found a material with 5-fold symmetry, what he really found was a material that had resolved the contradiction. The atoms had arranged themselves in a structure that was ordered but not periodic, a structure whose internal ratios were irrational, built on phi, and whose diffraction pattern showed the forbidden 5-fold symmetry precisely because the structure was not periodic. The quasicrystal did not violate the crystallographic restriction theorem. It transcended it. The theorem applies to periodic crystals. The quasicrystal was not periodic. It was aperiodic, like a Penrose tiling organized by the golden ratio instead of by rational lattice spacings. The golden ratio was not an incidental feature of the quasicrystal. It was the mechanism by which the quasicrystal existed at all. This is the thread that connects sunflowers, quasicrystals, Penrose tilings, and the E8 mass spectrum. In every case, the golden ratio appears because the system in question is operating beyond the boundary of periodic, rational order. Sunflower seeds pack periodically because the golden angle is the most irrational rotation. Quasicrystals form aperiodic atomic structures because icosahedral symmetry demands irrational spacing ratios. Penrose tilings fill the plane aperiodically because their tile proportions are irrational. And the E8 mass spectrum encodes phi because the quantum critical point is the boundary between ordered, periodic, and disordered chaotic phases of matter. And the symmetry that governs that boundary between two-dimensional critical quantum field theories and the exceptional Lie algebras is one of the deep, unexplained structural features of mathematical physics. It was not predicted by any prior principle. It was discovered by calculation, verified by experiment, and remains without a fundamental explanation. And the confirmation did not stop with Coldea's 2010 paper. It has continued widening and deepening across different materials and different experimental techniques. In 2020, two independent groups confirmed E8 particles in barium cobalt vanadate, BARCO2 V208, a different quasi-one-dimensional Ising chain antiferromagnet with a critical field around 5 Tesla. A team based at the University of Cologne and Shanghai Jiao Tong University used high-resolution terahertz spectroscopy and identified E8 excitations along with their multi-particle bound states. A separate team used the same technique on Cobalt Niobate itself, pushing the resolution further, and resolved the first 6 of the 8 predicted E8 particles at a temperature of 0.25 Kelvin and a critical field of 4.75 Tesla. Then, in 2021, a group using nuclear magnetic resonance and inelastic neutron scattering claimed to have identified all 8 single-particle E8 excitations in barium cobalt vanadate, along with multi-particle states. The golden ratio mass ratio between the first 2 particles has been confirmed in every experiment, on every material, with every technique. It is not a fluke. It is not an artifact of one crystal, or one measurement, or one lab. It is a structural feature of quantum matter at criticality. And here is where the story takes yet another turn, deeper and stranger than anything that has come before. The golden ratio does not only appear in the mass spectrum of quantum critical magnets, it appears as the quantum dimension of a type of quasi-particle called a Fibonacci enneon. And Fibonacci enneons may be the basis of the most capable computers ever built. To understand Fibonacci enneons, you first need to accept something strange about two-dimensional physics. In 3 dimensions, there are only 2 kinds of particles: fermions, which obey the Pauli exclusion principle, and bosons, which do not. When you swap 2 identical fermions, the quantum wave function picks up a factor of -1. When you swap 2 identical bosons, it picks up a factor of +1. Those are the only options in 3 dimensions. But in 2 dimensions, swapping 2 particles means moving them around each other in a plane, and the path you take matters. The wave function can pick up an arbitrary phase factor, not just plus or minus 1. Particles with this property are called anyons, from any phase, and some anyons are even stranger. When you braid them around each other, the operation does not just multiply the wave function by a number. It rotates it in a multi-dimensional Hilbert space. These are called non-abelian anyons because the order of braiding operations matters. Braid A around B and then B around C, and you get a different result than braiding B around C first and then A around B. The braiding operations are matrices, not numbers, and matrix multiplication is not commutative. Fibonacci enneons are the simplest type of non-abelian enneon. They have one defining property, expressed in a single equation. Tau times tau equals 1 plus tau. When 2 Fibonacci enneons come together, they can either annihilate into the vacuum, producing the trivial particle labeled 1, or fuse into a single Fibonacci enneon labeled tau. That fusion rule determines everything. The quantum dimension of a Fibonacci enneon the effective number of degrees of freedom it carries, is the positive solution to x squared equals x plus 1. That equation is the defining equation of the golden ratio. The quantum dimension of a Fibonacci enneon is phi. Exactly. The consequences cascade. The number of independent quantum states for n Fibonacci enneons grows as the nth Fibonacci number, proportional to phi to the power n. 2 anyons have 2 fusion channels. 3 have 3, 4 have 5, 5 have 8, 6 have 13. The Fibonacci sequence is not an analogy. It is the actual count of quantum states. And because the fusion space is non-abelian, braiding operations on Fibonacci enneons implement unitary transformations on those quantum states. In 2005, Michael Friedman, Alexei Kitaev, Michael Larson, and Zhenghan Wang proved a remarkable theorem. Fibonacci enneons are computationally universal. Braiding operations alone, without any additional resources, can approximate any quantum gate to arbitrary precision. This means a system of Fibonacci enneons, if it could be physically realized, would be a natural, inherently fault-tolerant quantum computer. The information would be encoded in the topological properties of the anyon braids, which are immune to local noise and decoherence. You would not need error correction. The physics does the error correction for you. In 2024, a team of researchers demonstrated non-abelian braiding of Fibonacci anyons on a superconducting quantum processor and published their results in Nature Physics. They realized Fibonacci enneons not as fundamental particles in a two-dimensional material, but as emergent excitations in a carefully engineered quantum circuit. They achieved the expected golden ratio quantum dimension with 98% average accuracy. The experiment confirmed that the mathematical framework works, that Fibonacci anyons behave exactly as the theory predicts, and that their quantum dimension is phi to within experimental error. Fibonacci enneons may also exist in natural systems. Theoretical analysis suggests they could appear in fractional quantum Hall systems at filling factor 12/5, where electrons confined to 2 dimensions in a strong magnetic field form exotic quantum states, whose excitations carry fractional charge and non-abelian statistics. This has not been definitively confirmed experimentally, but it remains one of the most actively pursued goals in condensed matter physics. So the golden ratio is not just hiding in the mass spectrum of E8 and Cobalt Niobate. It is the quantum dimension of the quasiparticle that may be the most natural platform for fault-tolerant quantum computation. The fusion rule of Fibonacci anyons, tau times tau equals 1 plus tau, is the quantum mechanical incarnation of phi squared equals phi plus 1. The same equation, the same recursion, the same number. Phi is not an ornament of quantum physics. It is structurally load-bearing. Remove the golden ratio from the fusion algebra of Fibonacci anyons, and you destroy their computational universality. Remove it from the E8 mass spectrum, and you destroy the integrability of the Ising field theory. In both cases, phi is not decorative, it is essential. Now step back and look at the full picture. The golden ratio appears in plant growth because it is the most irrational number, the one that maximizes aperiodic packing. It appears in quasicrystals because icosahedral symmetry, which violates crystallographic periodicity, is saturated with phi-fold geometry, and therefore with phi. It appears in Penrose tilings because aperiodic order in 2 dimensions requires the golden ratio to specify the tile proportions and frequency ratios. It appears in the E8 mass spectrum because E8 contains icosahedral symmetry through the subgroup H4, and the Coxeter projection onto the symmetry plane produces Gaussian circles whose radii encode phi. It appears in Fibonacci anyons because their fusion algebra is the quantum version of the equation that defines phi. In every single case, the golden ratio shows up not because someone went looking for it, not because a school teacher measured cadavers and declared a universal law, but because the mathematics of the physical system demands it. Phi appears wherever nature encounters forbidden symmetries, quantum critical points, aperiodic structures, and the boundaries of what periodic, rational capturable order can describe. This is the misconception that needs correcting, and it is the exact opposite of what you have been told. The common claim, repeated in countless YouTube videos and popular science articles, is that the golden ratio is everywhere in nature. That claim is wrong. Phi is not everywhere. It is emphatically not in the Parthenon, not in the Mona Lisa, not in the Nautilus shell, not in the human body. Those are fabrications. The golden ratio appears in very specific places where nature encounters extremal conditions, and only there. The difference between those two stories matters enormously. The pop science version, phi is everywhere, is a fairy tale that strips the number of all its real significance and replaces it with vague mysticism. The real version, phi appears at the exact boundaries where periodicity breaks down and something stranger takes over, is a precise and disturbing insight into the deep structure of physical law. The first story flatters your intuition. The second story should unsettle it. The question you should be asking now is not whether the golden ratio is in the Parthenon. The question is why E8 exists at all. The classification of simple Lie algebras is complete. It has been complete since Cartan finished his thesis in 1894. 4 infinite families and 5 exceptions. The infinite families are understood. They are the symmetries of standard geometric operations in spaces of any dimension. Rotations, reflections, symplectic transformations. They make intuitive sense. But the 5 exceptions have no such comfortable interpretation. G2, F4, E6, E7, and E8 do not correspond to symmetries of any familiar geometric object in any familiar number of dimensions. They exist because the classification, which is a rigid logical structure, following necessarily from axioms that nobody disputes, requires them. They are theorems, not choices. If you accept the axioms, E8 must exist, as inevitably as the number 17 must be prime. Denying E8 would be like denying that 2 + 2 = 4. The logical structure of mathematics forces its existence. But unlike the number 17, E8 has physical consequences. It governs the mass spectrum of quantum magnets at criticality. It constrains the gauge symmetry of one of the 2 consistent heterotic string theories. Its root structure encodes the golden ratio through the chain of icosahedral symmetry, 5-fold geometry, and the formula 2 cosine pi/5 = phi. Nobody designed this. Nobody chose it. The universe did not consult an architect. The laws of mathematics produce E8 as a necessary object, and the laws of physics selected as the symmetry governing certain critical quantum phenomena. The connection is exact, not approximate. The prediction was made in 1989 and confirmed in 2010. The mathematics has been checked and rechecked. This is not speculation. And the convergence of all these threads, phyllotaxis, quasicrystals, Penrose tilings, E8, Fibonacci enyons, points towards something that deserves to be stated plainly. The golden ratio is a structural constant of the physical world, not in the places where human beings projected it through wishful thinking, but in the places where the deepest symmetries of reality operate. It is embedded in the architecture of quantum mechanics, at the boundary between order and chaos. It is the quantum dimension of particles that may power the next generation of computation. It is the mass ratio predicted by a symmetry group that required a matrix larger than Manhattan to describe. And in every appearance, the reason is the same. Phi is the extremal point of irrationality, the number most resistant to rational capture, and nature selects it precisely where rational, periodic structure fails, and something fundamentally aperiodic is required. Zamolodchikov is now in his 70s. He holds the CN, Yang and Wei Deng Endowed Chair at Stony Brook University. His twin brother Alexei, who might have been the first person he told about the E8 prediction, has been dead since 2007. The paper that contained the mass spectrum, published in the International Journal of Modern Physics A, is historically difficult to access electronically, an almost absurd irony for one of the most important theoretical physics papers of the late 20th century. Shechtman's quasicrystals are now textbook material. The word quasicrystal has its own Wikipedia page, its own Nobel citation, its own chapter in every modern materials science course. But the man who saw the impossible pattern and reported it against the combined weight of the scientific establishment spent 10 years being told he was a disgrace to his field. Pauling, the man who called him a quasi-scientist, remains a towering figure in chemistry. Both things are true. Coldea's paper has been cited hundreds of times. The E8 result has been replicated across multiple materials. Nobody seriously disputes it anymore, but you almost certainly had not heard of it before this. You had heard about the Parthenon. You had heard about the Mona Lisa. You had heard about Nautilus shells and sunflowers and the divine proportion. The fabricated story, the one made up by a schoolteacher measuring corpses, is the one that saturated the culture. The real story, the one confirmed by neutron scattering at 40 millikelvin, remained in the journals. That asymmetry is itself a kind of answer to the question of how we relate to this number. We prefer the version of the golden ratio that flatters us, the version that says beauty is mathematical, and the ancients knew the secret code. That version is comfortable. It makes us feel like we are part of a grand design. The version that actually exists, the one where the golden ratio governs the vibrations of matter at the quantum critical point through a 248-dimensional symmetry group, whose existence is forced by the axioms of mathematics, is less comfortable. It does not flatter. It does not reassure. It says that reality, at its deepest accessible level, is organized around a number defined by its resistance to human comprehension, a number that resists being captured by any ratio, that sits at the extremal point of irrationality, that appears wherever the familiar structures of periodicity and order break down. The golden ratio was not in the Parthenon. It was not in the Mona Lisa. It was not in the human body. The places where you were told to look were empty. The number was somewhere else entirely. It was waiting at 40 millikelvin in the vibrations of cobalt atoms balanced on the knife edge between magnetic order and quantum chaos, encoded in the mass spectrum of E8. Zamolodchikov wrote down the prediction in 1989. His twin brother died in 2007 without seeing it confirmed. Coldea confirmed it in 2010. The universe had been obeying E8 since before there were physicists to measure it, since before there were human beings to project the golden ratio onto temples they did not build, since before the Earth formed around a star that was not yet born. The calculations have been checked. The E8 mass spectrum is what it is. The golden ratio is there, exactly where the mathematics said it would be, waiting for 21 years between prediction and confirmation, and for 4.5 billion years before that, in the quasi-crystalline structure of a meteorite drifting through interstellar space. Whether the universe has a favorite number is a question that sounds absurd until you look at the data. The data says it does, and the number it chose is the one defined by its refusal to be pinned down, the most irrational number governing the most exceptional symmetry, appearing at the most critical point in the most fundamental description of what matter does when everything stable falls away. That is not a fairy tale about Greek temples. That is what the equations say. And once you know it, you cannot unknow it. To truly understand the weight of Zamolodchikov's prediction, you need to understand the environment that produced it. The Landau Institute for Theoretical Physics, where Alexander worked through the 1980s, was one of the most remarkable concentrations of theoretical talent in human history. Founded in 1964 and named after Lev Landau, the Nobel Prize-winning Soviet physicist, it was located in the academic town of Chernogolovka, about 50 kilometers northeast of Moscow. During the Soviet era, it functioned as a kind of intellectual pressure cooker. Physicists who were not permitted to travel, not permitted to collaborate easily with Western colleagues, not permitted to attend most international conferences, channeled their formidable abilities into pure theory. The result was a series of breakthroughs in statistical mechanics, condensed matter physics, and quantum field theory that the Western physics establishment often did not learn about for years. Alexander Polyakov, one of the most influential theoretical physicists alive, was Zamolodchikov's colleague at the Landau Institute. The BPZ paper of 1984 by Belovin, Polyakov, and Zamolodchikov was written there. The paper demonstrated that the conformal symmetry of two-dimensional quantum field theories at critical points is infinite dimensional, generated by the Virasoro algebra, and that this symmetry constrains the theory so tightly that their correlation functions can be computed exactly. It opened an entirely new field of mathematical physics. Over 10,000 citations. It was in this environment, surrounded by the tools of conformal field theory and integrable systems, that Zamolodchikov asked his deceptively simple question: what happens when you perturb the two-dimensional Ising model at criticality with a magnetic field? The Ising model is the simplest possible magnetic system. Spins on a lattice, pointing up or down, interacting with their nearest neighbors. At the critical temperature, the system is poised between ferromagnetic order and paramagnetic disorder. The correlation length diverges. The system becomes scale invariant, described by a conformal field theory. But add a magnetic field, even an infinitesimal one, and the scale invariance breaks. The theory is no longer conformal. It becomes massive, meaning its excitations have non-zero energy. And the question is, what are those excitations? What particles exist in the spectrum of this deformed theory? The answer Zamolodchikov found was, by any measure, bizarre. 8 particles, not 7, not 9, 8, with masses in ratios that are not simple integers, not simple fractions, but algebraic numbers related to the root structure of E8. The lightest two particles have masses in the ratio phi, the golden ratio. This was not something anyone expected or even considered plausible before the calculation. The connection between the simplest magnet in physics and the most exceptional symmetry in mathematics was entirely unsuspected. Zamolodchikov himself, in later reflections, described the result as one of the most surprising he had encountered in his career. The mathematics forced it. He did not choose E8. The equations chose it for him. The 1989 paper is only 14 pages long. It is written in the compressed, almost telegraphic style typical of the Soviet theoretical physics tradition. There are no figures. The notation is dense. The key results are stated as conjectures, supported by consistency checks and bootstrap arguments, rather than rigorous mathematical proofs. The full proof of the E8 mass spectrum came later, pieced together by Zamolodchikov and others over the following decade. But the core claim that the perturbed Ising field theory contains 8 particles whose masses are governed by E8 was there from the beginning in those 14 pages. And for 21 years, it remained theoretical, a prediction without a test, a conjecture waiting for technology to catch up. The technology required was not exotic in principle. Neutron scattering had been used since the 1950s. Dilution refrigerators capable of reaching millikelvin temperatures existed since the 1960s. The missing ingredient was a material clean enough and well characterized enough to serve as a near-ideal, one-dimensional Ising chain, combined with the ability to tune it precisely to the quantum critical point with a transverse magnetic field. Cobalt niobate had been studied since the 1970s, but the specific combination of single crystal growth, ultra-low temperature neutron scattering, and high field magnet technology needed to observe the E8 excitations did not come together until Coldea assembled his international team at Oxford and Berlin. The BER-2 research reactor at the Helmholtz Zentrum Berlin, which provided the steady-state neutron beams for part of the experiment, was decommissioned in 2019. The machine that confirmed one of the most remarkable predictions in mathematical physics no longer exists. The window of experimental capability that produced the result has, in a sense, already closed at that facility. Other neutron sources remain operational at Oak Ridge, at the Institut Laue-Langevin in Grenoble, at J-Park in Japan, but the specific instrument configuration that Coldea used in Berlin is gone. There is a strange poetry in that. The prediction waited 21 years. The confirmation came, and then the machine that made it possible was shut down. The experimental evidence for E8 symmetry in quantum matter exists in data files and published papers confirmed by subsequent experiments on other materials and other instruments, but the original apparatus is no more. Like the Parthenon's original limestone casing, the instrument is gone, and what remains is the measurement and its implications. And the implications loop back to the question that has threaded through this entire story. Is the golden ratio a human invention projected onto a universe that does not care about our aesthetic preferences? Or is it a structural constant of reality, embedded in the deepest symmetries of matter, waiting at absolute zero for someone with a sufficiently cold crystal and a sufficiently powerful magnet to find it? The data has answered that question. The golden ratio was not projected onto the Parthenon. It was not projected onto the Nautilus shell or the human body. In all of those places, the projection was the entire story. But in Cobalt Niobate at 40 millikelvin, In the diffraction pattern of aluminum-manganese quasicrystals, in the spiral count of sunflower seeds, the golden ratio was not projected. It was found, not by anyone looking for it. Shechtman was looking at aluminum alloys. Coldea was studying magnetic phase transitions. Dowdy and Cuda were dropping ferrofluid onto a dish. In every case, the golden ratio appeared uninvited, forced into the data by the mathematics of the system, impossible to remove without destroying the physics that produced it. That is the difference between mythology and science. Mythology starts with the answer and finds the evidence. Zeising started with phi and found it in corpses by being flexible about what he measured. Science starts with the evidence and is compelled toward the answer. Coldea started with neutron scattering data and was compelled toward phi by the E8 mass spectrum. One process can produce any result you want. The other produces only the result the universe gives you. The result the universe gave is this. The most exceptional symmetry in mathematics encodes the most irrational number in its mass spectrum. And both of these appear in the vibrations of matter at the boundary between order and chaos. The golden ratio is real. It is not where you were told. It is not what you were told. It is stranger, deeper, and more unsettling than any myth about temples or paintings. And it has been sitting in the physics literature since January 8, 2010, waiting for someone to tell you the truth about the most misunderstood number in the history of mathematics. The truth is not that the golden ratio is the secret of beauty. The truth is that reality, at its most fundamental and least accessible level, is organized around a number that refuses to be caught. And the people who found it were not artists or mystics. They were a Romanian physicist at Oxford, a Russian theorist at Rutgers, and an Israeli materials scientist at the Technion. Between them, they endured decades of ridicule, rejection, and silence. And the number they found, waiting in the quantum fabric of matter, was the same number that Adolf Zeising hallucinated in corpses in 1854, and that the internet still attributes to the Parthenon. The difference is that this time, it is actually there.